Today we are going to talk about implementing pulse cooling technology into a plastic injection mold and the benefits of doing so. But first, let's just sort of set the stage. Cooling in injection molding.
I
It's
don't-
huge, right? Our sources suggest it can eat up, what, nearly 80% of the entire cycle time?
That's absolutely right. 80%. It's easily the biggest time sink in the whole process.
Oh.
And if you don't get that cooling optimized, the consequences hit you hard and fast. We're talking defects, warping, sink marks everywhere.
Parts just not coming out right.
Exactly. Differential shrinkage, poor shaping. Plus, your mold trials drag on forever. It really impacts, your final part quality and how efficiently you can actually produce anything.
Okay, so if it's that critical, why does it sometimes feel like an afterthought in shops? What are the typical ways people handle cooling now, and what are the headaches?
Yeah, it's a good question. Maybe it's just not as flashy as, say, resin chemistry, but the problems are real. Two common methods you'll see are continuous flow and warm water cooling. With continuous flow, folks often just manually throttle back the coolant flow. Sounds simple, but it actually distorts the mold surface thermally.
How so?
Well, it creates uneven temperatures on the part, weird heat gradients, which basically builds stress into the plastic. So you get warp. And the adjustments, they're always reactive, after you've already made bad parts.
Mixing it after the fact, not ideal.
Not at all. Then you've got warm water cooling. People use this sometimes to pre-warm the mold, then to pull heat out.
Okay, that sounds a bit more controlled.
You'd think so.
Yeah.
But it often leads to uncontrolled surface temperatures, very unpredictable. Heat doesn't really transfer effectively until the mold surface gets quite a bit hotter than you'd want.
Ah.
This causes issues like poor fill at lower temperature. Basically, the plastic freezes off too soon. And you constantly fight temperature drift.
So it's still chasing the problem.
Still chasing it.
Oh.
Both methods mean constant tweaking, adjusting based on part quality that's bouncing around.
Yeah.
Lots of adjustments, lots of scrap. It's costly.
It definitely sounds like the industry needs something, well, smarter, more precise, proactive maybe.
Precisely. And that's where this pulse cooling idea comes in. It's a fundamentally different approach.
How is it different?
The core principle is controlling the actual mold surface temperature directly, not just guessing based on the water temperature going in or out.
Okay, how do you measure that?
With embedded sensors.
Yeah.
Right there in the core and cavity, feeding back real-time temperature data.
Ah, direct feedback.
Exactly. The controller takes that sensor info and tells a very fast-acting valve what to do. It delivers a calculated pulse of coolant.
The pulse.
Yeah, a short, specific burst using the coldest water you have at maximum flow rate, but only for the exact amount of time needed to remove the excess heat from that specific cycle.
So it's tailored to each shot. That sounds much more dynamic. It adapts then to cycle time changes, different plastics, ambient temperature shifts.
Completely. It automatically compensates for all those variables, cycle time, the heat coming in from the melt, ambient conditions, even changes in your plant's cooling water pressure.
Okay, interesting. You mentioned a pulse of coolant. What happens between pulses?
That's key. It's what we call the soak time. After that cooling pulse, the system actually stops the flow completely during the cure or hold time.
No flow. Why?
It allows the heat gradients within the steel to dissipate naturally. The mold reaches a state of thermal equilibrium. It becomes much more uniform in temperature.
I see. So the starting point for the next shot is much more stable and predictable.
Exactly. More uniform, predictable, repeatable. And that translates directly into significantly higher, more consistent part quality.
Okay, that makes sense for quality. What about the other side? The efficiency, the costs, what are the tangible benefits for a molding operations, bottom line?
Oh, they're substantial. On the production side, you're looking at consistently higher output, faster cycles, because you're cooling more effectively, genuinely optimized cycles, plus a really drastic reduction in the load on your chiller system. And power consumption is tiny, maybe 10 watts a zone, like $10 a year per zone to run.
Wow, okay. That's significant. And quality-wise?
Consistently higher quality, like we said. You basically eliminate that thermal drift, which cuts down warp, sinks, distortion, inconsistent filling, all those headaches. You get precision control, constant monitoring.
And operationally, any advantages there?
Yeah, quite a few. Faster warm-ups, quicker recovery if the cycle gets interrupted. It uses minimal water overall because of the pulse approach. The units usually mount right on the machine, so no extra floor space needed. And maintenance is really low.
Yeah.
No external heaters, motors, or pumps involved in the cooling control itself. It adapts to pretty much any mold size, too.
And I saw it's not just one setting, right? There are different categories.
Correct. It caters to different needs. Low temperature molding, combinations, even ultra-high temperature resins. It's adaptable to the material you're running.
So it really brings a level of intelligence and precision to cooling that seems, well, long overdue.
It's about moving from reactive adjustments to proactive, data-driven control.
It's clear that intelligent cooling strategies like this offer immense value for modern plastic processing. It's not just about making parts anymore, but making them faster, better, much more efficiently. If you have a new project, reach out to True Position Plastics. They can help you with any and all things plastic injection mold related.